Hi, in this one we are going to start proving the DeMoivre-Laplace local central limit theorem. It's a more or less elementary but a little bit tedious proof, so I cut it in 3 parts. This is part 1. The proof of DeMoivre-Laplace central limit theorem is of course based on Stirling's formula, which we covered in a previous video. Here is Stirling's formula again. And I remind everybody that at that time when we proved this, we actually didn't find this constant here. We just said that there is a constant which we can put here with which that formula is true. So actually I'm going to use pi hat for that constant, and at the end of this couple of videos we're going to see that pi hat is indeed pi. But for now we don't know that. So I'm going to prove this with the assumption that there is a pi hat constant there. Okay, so the proof starts with expanding on this mass function. So what is this mass function? This is of course n choose k, p to the k, q to the n minus k. And we think of n as something being large and k being closer to np than square root of n times an. Okay, so let's write out the factorials. So there are a couple of factorials in n factorial. So I have n factorial, then k factorial, n minus k factorial, and then we have p to the k and q to the n minus k. That's all the terms we have in there. And now we're going to plug in Stirling's formula with an unknown pi, for all of the factorials. So we have 3 factorials here. All of them will be substituted using Stirling's formula. Okay, so the first one is n factorial, and n factorial can be replaced by n to the n over e to the n square root of 2 pi hat times n, and we can do this with a price of 1 plus capital O of 1 over n. Okay, so everything I do has an error, and this error is a multiplicative factor of 1 plus something in the order of 1 over the actual number I'm substituting the factorial of. So if I want to do that, then n factorial becomes n to the n. Let's use some colors here. We have colors. So n factorial is n to the n over e to the n, and then square root of 2, and I'm going to use pi hat n. This was n factorial. Okay, now let's do the same with k factorial. Notice that k is in the order of np. K is actually not very far from np. It's at most root n times something smaller than n to the 1/6 away from np. So k is still large. It's still in the order of np. And I can apply Stirling's formula on that and put k to the k over e to the k and over let me do this fraction in purple, and over square root of 2 pi hat and k. So this was k factorial, and I don't forget about some errors which come at the end. Okay, and finally I have n minus k factorial. So let's put in n minus k factorial. So that is n minus k to the n minus k over e to the n minus k and square root of 2 pi hat n minus k. So this was n minus k factorial, and the previous was k factorial. And then I also have the p powers and the q powers. So let's put in those as well. P to the k and q to the n minus k. And then finally I have the error terms. Again, the error term comes as a multiplicative factor of 1 plus something in the order of 1 over n. So 1 plus capital O of 1 over n, and again the reason for 1 over n is that n is clearly in the order of n, and then k is also in the order of n because it's close to np, and n minus k is then close to nq, so that's also in the order of 1 over n. So this error terms captures all three errors from Stirling's formula. Okay, now the first good news is that the exponentials all cancel out. I have e to the positive n, e to the negative n, e to the positive k, e to the negative k, and that's it. So in fact the exponentials all cancel out. That's the first good news. I also have a cancellation of one of the root pi hats, and if I just collect all the terms, then I have a 1 over, so actually it's even one of the 2's will cancel out. So I have 1 over square root of 2 pi hat downstairs. Then I have a okay, I'm going to write out a couple of terms, and then we'll see that it's actually true. So I'm going to write some funny way of dealing with all this, and then I'm going to convince everybody that what I wrote is valid. So I have an n minus k over nq to the power of n minus k. Then I have a k over np to the power of k. Then I have down here a n minus k over nq to the power of 1/2, and then a k over np to the power of 1/2, and the error term. And now let's see that this is actually valid. So can I find n to the n? Yes, n to the n is here. N to the n is here. Can I find the square root of n down here? So I have a square root of n there. I have a square root of n in the denominator of the denominator, so these two actually cancel out. I have another square root of n down here which goes up there, and that's what I had before. So the square root of n is there. The exponentials are gone. Can I find p to the k? Yes, here is p to the k. Can I find q to the n minus k? Yes, here is q to the n minus k. I also have some q to the 1/2, but that cancels with that square root, so these guys cancel. I have p to the 1/2, but those guys cancel again, so that's fine. What else am I looking at? I need to look at k to the k, which is here, n minus k to the n minus k, which is there. I have the square root of k, which is here, the square root of n minus k, which is there, and the root 2 pi hat is also fine because I have 1 up here and 2 down there, so that's 1 down there. So all of the terms match up, so it's absolutely fine. And the next step I need to do is I need to collect these in a slightly different fashion. So again, the main idea is that k is close to np. K is close to np, relatively close to np. So in the statement, k minus np cannot be larger than square root of n times something small, relatively small, like this is smaller than n to the 1/6. Okay, so the idea I want to make use of is that k is more or less close to np, and therefore I'm going to rewrite this whole formula in the following way. So 1 over root 2 pi hat npq, that's the constant in front, and then the first parenthesis here I'm going to write as 1 minus k minus np over nq, and this is raised to the n minus k. The second part of this I rewrite as 1 plus k minus np over np, and this is raised to the power k, and then do the same on the other side, on this other term. 1 minus k minus np over nq raised to the 1/2, and 1 plus k minus np over np raised to the 1/2, and the error term 1 plus big O of 1 over n. Okay, so again I need to convince everybody that this is valid, and just make a common denominator here. If you do a common denominator, then you have nq plus np, so that's n, and you have the minus k, so n minus k. If you make a common denominator there, you have np plus k minus np, so that's k, and the same thing happens here and there. Now, what was the reason I did that? The reason was that these guys, let me pick a nice color here, these guys, k minus np, again, k minus np is root n times something smaller than n to the 1/6. So root n is n to the 1/2, n to the 1/6 coming to it, or something smaller than that. It's still much smaller than n. So k minus np is much smaller than n. And therefore, if I divide k minus np by nq, or k minus np by np, these things will be small. These guys are small as n goes to infinity, at least in the range of the k I'm looking at. So it's always good to have something like 1 minus small times 1 plus small, 1 minus small, 1 plus small. This is always a useful form, and that's exactly what we're going to make use of. And so the rest of the argument will be split in two parts. This term I'm going to call term 1, and this term I'm going to call term 2, and we're going to do some analysis on both of these terms. So that's coming in the next video.